Alright, in this video we're going to learn how to do a two-proportion z-interval and z-test. Alright, so an example. Do men and women wear seatbelts the same percent of the time? In order to find out, we take a simple random sample of 200 male drivers and another simple random sample of 250 female drivers. We find that there are 146 men that wear their seatbelts regularly and 203 women that wear them regularly. Is there a significant difference between the two genders? What is the difference, if any? So we don't know yet how to solve all of this, but you can see this has two different samples. Okay, so we have a sample for men, we have a sample for women. So this is going to be a two proportion test. All right, so the p hat for males is equal to 145 out of 200, which gives me 73%. And the p hat for females is 203 out of 250, which gives me 81.2%. If we were going to do a test, we would find the difference between them, which is 0.082. Our null hypothesis would be the probability or the proportion of males is equal to the proportion of females that wear seatbelts. Our alternative would be the proportion of males is not equal to the proportion of females that wear seatbelts. All right, and we'll learn more about this. A two-proportion z-interval. We can create a confidence interval for the difference between the two proportions. Okay, so we're always working with the difference. So conditions for both interval and a test. All right, so remember we have to double the ones for a one proportion. So we have two independent simple random samples. Okay, the key is that it's independent. So you might say the sample for men is stated simple random sample, which is independent from the other sample for women, which is also stated simple random sample. Or you might make a statement about it being random and then another statement about it being independent, however you choose. All right, n times p has to be greater than or equal to 10 for both different sets. So we have two samples, so n1 times p hat 1 has to be greater than or equal to 10. n1 times 1 minus p hat 1 has to be greater than or equal to 10. And then for the other set, n2 times p hat 2 has to be greater than or equal to 10. And n2 times 1 minus p hat 2 has to be greater than or equal to 10. We also have to have that 10% condition, so the population has to be greater than 10 times the sample. That's for each sample, so we have to do that twice. Once our conditions are met, we say conditions met, use a normal model, and we're going to do a two proportion z-interval or a two proportion z-test. All right, since the normal model is being used, we need a mean and a standard deviation, or standard error if we're using p hats. So mean is p hat 1 minus p hat 2, it's the difference. The standard error, we find the standard deviation of one sample the exact same way as we have been. But when I'm finding the standard deviation of the difference, okay, it's this each standard deviation squared added together. So we could just do all the work at one time. So it's the square root of p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 over n2. And then my confidence interval follows that same basic formula, statistic plus or minus your critical value times the standard error. So my statistic is the mean piece, that difference between the two proportions. So p hat 1 minus p hat 2 plus or minus my z star value, which they're going to be the same z star value. So if it's a 95%, a 90%, a 99%, you should have those memorized. Otherwise, you can find them in your calculator under inverse norm, times the standard error, because I'm using p hats, and that will give me my two intervals. All right, our conclusion is basically the same, a little bit different. So we are blank percent confident that the difference in the proportion of whatever it is we're talking about, and whatever else it is we're talking about, is between blank and blank percent. All right, so let's do an example. College students were randomly selected and asked how much alcohol they consumed on a weekly basis. Over a certain amount of alcohol consumed was considered binge drinking. Out of 5,348 males surveyed, 1,392 were identified as binge drinkers. Out of 8,471 females surveyed, 1,748 were identified as binge drinkers. What is the difference in the proportion of male and female binge drinkers? Use a 95% confidence. So, our p hat for males is 1,392 divided by 5,348, which gives us 0.2603. The p hat for females is 1,748 divided by 8,471, which gives us 0.2064. Our conditions that we have to check. Both samples are stated simple random samples, so both are random. Male and female college students are independent of each other. Okay, you could combine those two conditions if you want. N for males times p hat for males equals 1,392, which is greater than or equal to 10. N for males times 1 minus p hat for males is 3,956, which is greater than or equal to 10. I'm going to check the same thing for females. So N of females times the p hat of females is 1,748, which is greater than or equal to 10. N for females times p hat for females is equal to 6,723, which is greater than or equal to 10. So those all check out. And then my 10% condition. So there are more than 53,480 males and 84,710 female college students. So conditions are met. We're going to use a normal model, and we're going to do a 2 proportion Z interval. Our work is going to be our statistic, which is the difference in males and females. So I'm just subtracting those p hat values, plus or minus my Z star. Well, I'm doing a 95% confidence, so my Z star is 1.96, times the standard error. So I'm standard deviation with p hat values. So p hat for males was 0.2603. 1 minus the p hat of males is 0.7397 over N, which was 5,348, plus, okay, I'm always adding in here because everything's really being squared, and then I'm taking the square root, so plus the p hat for females times 1 minus the p hat for females divided by N for females, which is 8,471, which when I put this all in my calculator and work it out, I get 0.03935 to 0.06851. All right, so I'm going to erase some of this so I can write my conclusion. All right, my conclusion is we are 95% confident that the difference in the proportion of men and women binge drinkers is between 3.935% and 6.851%. A 2 proportion Z test. We can compare 2 proportions together. Our hypothesis, our null hypothesis, would be P of 1 is equal to P of 2. Our alternative hypothesis would be that the proportion of 1 is less than, greater than, or not equal to the proportion of 2. Now sometimes you might see that moved over, so it would be P, the proportion of 1 minus the proportion of 2 equals 0. And then the proportion of 1 minus the proportion of 2 is less than, greater than, or not equal to 0. So just be prepared. You could see it that way maybe on your AP test. All they did was just move it over so that it would look like a difference. The conditions are going to be the exact same as we had for a confidence interval. All right, we're going to say conditions met, normal model, a 2 proportion Z test if we're doing a Z test. All right, mechanics. All right, so our null hypothesis is P1 equals P2. So we must assume that the null hypothesis is true until proven otherwise. So if P1 is equal to P2, then we should really combine P hat 1 and P hat 2 so that we can have more info about the true proportion. So this is called pooling our sample proportions together. So if I have P hat 1 equals some number that I have, the sample divided by the sample size, P hat 2 equals the sample divided by the sample size, then what I would do is I would just take that sample value plus the other sample value and divide by the two sample size combined. And that would give me my pooled P hat. The mean when I'm doing a 2 proportion z test is still P hat 1 minus P hat 2. But the standard error, I'm going to be using the pooled P hat. So it's pooled P hat times 1 minus the pooled P hat divided by the first sample size plus pooled P hat times 1 minus the pooled P hat divided by the other sample size. My test statistic is found by doing the mean divided by the standard error. So P hat 1 minus P hat 2 over the square root of, and all of these P hats in the square root, I'm using the pooled P value. So then our P values are the same. Okay, so if our P is lower than our alpha, we reject the null hypothesis. And then remember, if it's a two-sided sample, if it's a not equal to, you have to do 2 times the probability that z is greater than the absolute value of your test statistic. And then our conclusion, we have 2 sentences. So it's the same first sentence. We reject or fail to reject the null hypothesis because our p-value is greater or less than our alpha, same as what we've been saying for a 1 proportion. Our second sentence is we have sufficient or insufficient evidence that the percent of blank is blank the percent of blank. Okay, so we'll see a little bit more when we do a problem in context. Alright, so back to the example from the beginning. Do men and women wear seatbelts the same percent of the time? In order to find out, we take a simple random sample of 200 male drivers and another simple random sample of 250 female drivers. We find that there are 146 men that wear their seatbelts regularly and 203 women that wear them regularly. Is there a significant difference between the two genders? Assume conditions are met. Alright, so I'm going to start by finding all my values. So p hat of m equals 146 divided by 200, which is 0.73. P hat of f equals 203 divided by 205, which equals 0.812. And then to get my pooled p hat, it would be 146 plus 203 divided by 450, because 200 plus 250 is 450, which gives me 0.776. Alright, my null hypothesis is that the proportion of males is equal to the proportion of females. My alternative hypothesis is that the proportion of males is not equal to the proportion of females. They didn't say, is there significant evidence that women wear them more regularly or that men wear them more regularly to help us to determine if it should be a less than or a greater than. So we're going to do a not equal to. We're going to say the conditions are met. We're using a normal model and we're doing a 2 proportion z test. So to find z, it's going to be our mean, which is the difference between the two p hat values. So 0.73 minus 0.812 divided by the standard error using the pooled value. So 0.776 times 1 minus that, which is 0.224, divided by 200, plus the same top piece, because I'm using the pooled p hat value, but this time it's divided by the other n value, which is 250. When I plug that all in my calculator, I get negative 2.072. So that's my z-score. Now I need to find my p-value. Well, it's a two-sided test. It's a not equal to. So it's 2 times the probability that z is greater than the absolute value of negative 2.0272. Just 0.72. So when I plug that in my calculator, I get 0.0383. Remember, you're doing a normal CDF. I'm doing a greater than. I'm using the absolute value, so I'm going from 2.072 to 9999999. I'm using a mean of 0 and a standard deviation of 1, and I'm getting that p-value. Then I'm multiplying it by 2, and you get 0.0383. So my p-value is pretty low. I'm assuming an alpha value of 5% since they didn't give me one. So we would reject the null hypothesis because our p-value of 0.0383 is less than our alpha value of 0.05. Therefore, we have sufficient evidence that the true percent of males wearing seatbelts is not equal to the percent of females wearing seatbelts.